My name is Jan Harzan. I'm the Executive Director for MUFON. We are a scientific research organization that basically collects sighting reports from the public and then goes and investigates them. Our mission statement as an organization is the scientific study of UFOs for the benefit of humanity, and we have three primary goals. We investigate UFO reports, we promote research into the UFO subject, and we educate the public on our findings. MUFON is really more just left of center, where we try to take a scientific approach by collecting the data first off, and then reviewing the data, investigating the data, and making sure that what we're seeing is actually something that's truly an unknown. We have 3,000 members worldwide. Many scientists, physicists, PhDs, metallurgists, biologists, all the way down to just the average citizen who really wants to get involved. Some of those have chosen to become field investigators, and they go through our field investigative training courses. They become part of the team in their state or country where they reside, and they actually get engaged in going out and meeting this phenomena head on. We receive about 500 to 1,000 reports per month from around the world. Field investigators will take the case, generally review it, try to come up with a hypothesis, checking star charts, and we'll go put an investigation in place to determine what exactly happened. We've recently formed a science review board, and that board is made up of scientists from around the United States and around the world to review some of our more significant cases and try to render an opinion on them. What we'd like to do is be more outbound, more outspoken in terms of the really true UFO cases. So MUFON is moving forward with this approach, and we'll be publishing papers in these different areas to allow the general public and even the scientific community to be able to be challenged by what we're finding. That's the strength of MUFON as an organization, is being really the truth seekers of the UFO field.
Good afternoon. Our next speaker, Greg Meholic, currently works as a senior project engineer for the Aerospace Corporation, supporting space launch vehicle concept development and advanced propulsion system technology for the United States government. Prior to his current position, he supported upper stage cryogenic rocket engine launch activities, performance reviews, and hardware design assessments for most of the United States space launch systems, contributing to over 4 successful missions. His work also included defining launch vehicle operational requirements, launch systems and designs, and leading numerous project teams for both NASA and DARPA-funded studies regarding the capabilities and testing of advanced engines. Here to talk about advanced space propulsion concepts for interstellar travel is Greg Meholic.
Well, thank you very much. So I just want to thank Jan Harzan for inviting me here, and this is my first exposure to MUFON and any of the that type of conference. I haven't had an opportunity to interact with anybody just because I had family events on both sides of today and yesterday. So I just really want to thank Jan for allowing me the opportunity to speak to you today. As you probably heard from the introduction, I'm really not affiliated with MUFON, but what I do is rocket science. And so what I'm here to share with you today is a little bit about some concepts that are being studied right now by people around the world to deal with space propulsion systems for interstellar travel. So this presentation is going to focus more on us going to the stars rather than whoever's in the stars coming to us. But it might give you some idea of the kind of technologies that other beings or other systems might have to consider in order to take the journey from their home to here, because no matter what happens, physics is still physics around, throughout the universe. So what I'm going to talk about is a very high-level evolutionary information-only overview of some of the various propulsion technology concepts that, if obviously sufficient development, which means money and time, may lead mankind to the stars. So I'm only going to talk about candidate vehicle systems for a primary interstellar propulsion system, meaning that You can go to the engine room of some starship and open it up, and what do you see? Okay, so I'm not going to talk about any attitude control, getting from Earth to orbit, no electric systems, no sails, or no beamed energy. And a lot of those latter ones, there's been some press recently, but we're not going to talk too much about any of those. I'm also not going to I'm not going to try to give, assume, or imply any recommendations on specific missions to go to different stars. Because believe it or not, there's actually been a lot of people over the past several decades that have done interstellar mission design. How long it would take to get to Alpha Centauri using a specific kind of antimatter engine, or what kind of trajectories to take to minimize travel time. So those people have already done that kind of work, and there's a huge body of literature in that. And so obviously I'm not going to talk about developmental timelines or schedule, because without any kind of cost estimation or understanding of some of the technology needed to do this, we really can't say how long it would take to develop these things. We can only make a guess, right? And obviously I'm not going to talk about everything. The ones that I'm going to talk about here to keep the time within the time I have for this talk are going to be the ones that have had some level of press in the past couple years or even months, or that have some significant data behind them to say that there might be something real there, okay? So these are the kind of chapters of the talk. You can see we're going to start out with the ultimate space mission and kind of move down through rocket science basics. And so what that's going to do is kind of give you an idea of what we in the propulsion world have to look at when we measure one type of propulsion system against another. Kind of, equivalents of like miles per gallon and, emissions and that sort of thing, but on a rocket science level. Then we'll go down through some of the concepts you see there, and number 7 is my favorite part, physics-based concepts, and that's when we start getting into the real fun stuff. And then finally, experiments, and then some closing information. Before I start that part, I want to go back and point out that on this title slide is my email address here, okay, orionstar2209@yahoo. Please email me. I would be happy to send you a copy of this talk. I think it's also going to be available on DVD and whatever, but let me know you saw me here at this conference. Otherwise, right to spam you go, okay? But I'd be happy to send you a PDF version of these charts, okay? So, okay. We'll move on to the ultimate space mission. Okay, when I put this talk together back in 2008, giving it to the American Institute of Aeronautics and Astronautics, there was a lot I had to try to consider of what to do. And so I tried to figure out a way to say, well, why don't I make up this fictitious mission where I can start looking at whether or not propulsion systems I'm going to talk about in this talk can actually perform the mission, some form of mission, right? So I came up with this pulled out of the sky, complete random mission for humans to travel to the stars and return to Earth within what I'm calling a reasonable fraction of a human lifetime, about 15 years, okay? So the reason I picked 15 years is because in order to undertake a mission like this, someone's going to have to train for a majority of their life. So let's say they embark on the mission when they're 45 and they've spent 45 years training, or however many years training. They can spend 15 years doing the mission, whether or not it's 5 years out to a star, 5 years there and 5 years back, or 1 each way and then 13 years there, whatever the case is. But then when they come back and they're 60, they still have a lot of natural life left in them to share their knowledge in person and share and further scientific knowledge for the human race. So why would we want to do anything like this? Okay, well, there's a couple reasons why we would want to venture beyond our solar system. Well, the first is we love to explore, right? I mean, that's just our nature. We also want to visit the Kuiper Belt and the Oort cloud, and there's a mission that we already know is on its way there, New Horizons, and I'll talk about that in a little bit. So we'd like to go see what's out there. And if we go further than that, we can investigate the interstellar medium. What is between stars? We really don't know. All right, and so, how does that interstellar medium influence what our sun does, and how does what our sun does influence what Alpha Centauri and other stars do? There's a space weather there, but on a galactic scale. We'd like to observe nearby solar systems, obviously. Let's go somewhere and see these planets and put a lander down where we, instead of looking at them through powerful telescopes, let's go do some real sensing. Obviously, to look for other Earth-like planets, we found a couple of those already, and at least we think, based on the light we get back from them, and also to search for life. That would be the ultimate find, is searching for life beyond the surface of the Earth here. Okay, so where are we in the solar system? Well, Before I talk about the solar system, I need to go over a couple terms. And some of these terms I'm sure you've heard being in this particular area of interest, like the speed of light. Okay? The speed of light is 186,000 miles per second, or 3 times 10 to the 8th meters per second if you're Canadian. And the animation that I have shown right there is a real-time animation of how long it takes a signal to go from the Earth to the Moon, a radio signal. About 1.25 seconds, and it goes 250,000 miles or so. Okay? So that gives you some idea of that. Now, if you continue that line all the way to the right, and you extend that out for 1 year, and you put it at the scale of what the real Earth and Moon are, and not just on the chart there, you get the distance of 1 light year, and that's 63,000 astronomical units, give or take, okay? And an astronomical unit is the distance between the Earth and the Sun with the Earth's mean orbit of 93 million miles, the number we've learned from elementary school. So 93 million miles, 1 astronomical unit, 63,000 of those is 1 light year, okay? And that gives you some scale for what I'm going to show you on the next chart here, okay? What I'm showing here on this chart in the bottom is the Sun at the far left. On the far right, you have Alpha Centauri with the box there that says 271,000 astronomical units. That's how far Alpha Centauri is, or that star system. The halfway point is 135,000, and it doesn't look halfway on there because it's a logarithmic scale, okay? So that's why it looked a little funny. So obviously, we are here, 1 astronomical unit, okay? As we go further out, we see the little green pentagon, the pink triangle, and the red plus. I'll talk about those in a second. Because those mark the actual interstellar spacecraft that we've sent to orbit, or not to orbit, but into space already. So the human race has actually sent 5 interstellar spaceships into interstellar space, 3 of which I have shown here because I couldn't fit the other 2 on, and the information about those is given at the right above them. Pioneer 10 was launched in 1972. It's currently at a distance of 107 astronomical units. It's whipping along at a breakneck speed of 27,000 miles per hour, which in all practical terms sounds really fast compared to the 405, but it's 4,000ths of 1%. 4,000ths of 1% the speed of light. Okay, so that may seem fast to us, earthly beings, but when you compare it to the natural speed of things in nature, it's pretty darn slow. Voyager 1 launched a few years later at 127 astronomical units at 38,000, so it's going a little, 10,000 miles an hour faster, but again, 5,000ths of 1% the speed of light, kind of piddly, all right? Interestingly enough, and I always forget which one is which, but one of these, Pioneer 10 or Voyager 1, is heading towards Aldebaran in the constellation of Taurus, and it'll take 2 million years to get there, okay? The other one is heading towards Alpha Centauri, and it'll take 75,000 years to get there. So the human race can evolve 2.5 to 3 more times by the time that probe reaches Alpha Centauri. Okay, kind of weird. All right, now New Horizons. I mentioned that earlier, and this is kind of near and dear to my heart. One of the 4 dozen missions that I had the pleasure of working in the industry that I work in was supporting that launch. So I was actually in mission control looking at the upper stage engine that sent New Horizons on its way. Back in 2006. And so obviously, this is a little bit outdated. It's at 31 astronomical units, at least back in February, so it's obviously past that now. February is when I did the last updates to these charts. 33,000 miles an hour, and we all know what it was designed to do, right? Whiz past Pluto and then head on its way out, which it's already done. An interesting tidbit about this particular launch. It was going up on the most powerful rocket that the United States had, called the Atlas V, in the 551 configuration. That particular rocket can loft tens of thousands of pounds of payload to orbit. That's what it's designed to do. But instead, it launched New Horizons, which weighed 1,200 pounds. So that was the fastest thing to ever leave the Earth's surface was the New Horizons launch. And another tidbit of information, obviously it was launched 2006. We got the results this year in 2015, a 9-year mission. The launch window for New Horizons was 1 second. If they missed that launch window by 1 second, it would have extended the mission by 2 more years. And right at that second, the engine's lit, and obviously, history was made in about 2 months ago. So, so we're doing good there. Okay, so anyway, we've sent these things on their way. So let's say we go back and we bring it back into context of this human mission, this 15-year mission. Well, where could we go if we had 15 years to go play around interstellar space? Well, this chart I have up here shows the sun and then a 12 light year radius out away from the sun of what different stars are out there. So along the side are the stars that are listed on that chart, and the ones in green that you might be able to see are the ones that we have identified planetary systems around, okay? And there's 5 of them there. Oh, actually, I'm sorry, 3 other than our sun. So, you know, we do have places to go. We can put resorts out there and Walmarts and all sorts of other things. There's places to go, things to do, things to see, rather than just, you know, one destination. So, you know, we have our choice. Okay, the challenges of human starflight. And interestingly enough, this may be challenges from other things, you know, other beings that might be doing this, you know, coming to our end. You know, they might have these same challenges. So the first one is spacecraft velocity limitations. All right, now there's a fancy looking graph up there, but I'm going to tell you what this means in just a second. As I showed you before, the speed of the interstellar spacecraft that we've launched already, ridiculously slow, okay? If we want to get to a star called Tau Ceti in 40 light years, just by doing the basic math, we would need to go 30% the speed of light, or roughly 202 million miles an hour. All right, now if you remember, the fastest thing that we had was going in the 50s thousands or 30,000 miles an hour. So we have a couple more zeros to add. So we need to be around the tens of percent the speed of light, or faster, if we're going to do anything remotely close to going to another star within a reasonable fraction of a lifetime. So what I have on the chart is at the very top I have fraction of light speed, which goes from 0 to I think 30% on the top there, distance in light years. And this is basically a graphical representation of what I mentioned in the bullets. But along the bottom is velocity in this particular chart's kilometers per second. Okay, now the velocity, the line of where you'd fall on that velocity chart, I tried to find the thinnest possible line in PowerPoint and put it on there. And we're not even on the plot. That's how slow our spacecraft are going right now compared to what we need to be doing. So that's an issue, okay? The next one, special relativity. All right, you probably have heard of all this. There's all kinds of crazy things that happen when you start getting close to the speed of light. Time slows down, length gets shorter, mass increases. Those are big deals, okay? Because if we start going to this, if we get towards the speed of light, we have to deal with all of these issues that Einstein said you will have to deal with, and we know that we have to deal with because they're all scientifically proven. The first one I'm going to talk about is mass increase. Okay, basically I said it before, the faster you go, the more your mass apparently increases, such that if you want to go the next increment of velocity faster, you need more energy. And then to go the next equal increment faster, you need twice as much energy, and so forth and so on. So you have this exponential effect of the energy on the y-axis versus velocity on the x-axis. And you see this green curve coming up to this dotted red line, and the green curve will never touch the dotted red line. That basically says that no matter how much energy you put into moving something, you will never get it to accelerate to the speed of light. You can always get 99.999, a bunch of nines, but never the speed of light. The only thing that moves at the speed of light are photons, and they move only at the speed of light. So there's an interesting play off of that, and we'll talk about that a little later. But the point being is that particles with mass can never be accelerated to the speed of light. We know this to be true. The next one is time dilation for special relativity, and this is one that's kind of freaky, is that basically moving clocks run slower. Believe it or not, the time that you're experiencing driving on the highways is different than the time experienced from people that aren't driving on the highways. Even at that minuscule velocity level, there is a noticeable difference. It's been experimentally proven. But the point about this is that if Joe is an astronaut and he has a little boy, and Joe travels for 1 year in space at very close to the speed of light, to him, 1 year later, he's a year older. But his son is like 30 or 40 years older, or maybe even deceased by that time. Okay, so what does this all mean? Again, this is all scientifically proven. And if you saw the movie Interstellar, they really wrapped a big bow around this one, okay? The time dilation thing. So we know that this all works, and we've experimentally done this. But what this means is that, let's say we're traveling at 99% the speed of light on the way to Alpha Centauri, and we get to the halfway point, and we radio back to Earth and say, hey, we're at a halfway point, everything's good. All right, well, by the time those signals reach the Earth, everybody that was associated with your mission is dead. Okay, so there's an issue there, all right? So even though time progresses normally for the people moving, seemingly, it really is different for the people that are stationary. So we have to deal with that, okay? And when we start doing these light speed travels, we have to consider, okay, when we get home, does anybody care or even know about where we're coming from, all right, from a mission standpoint? Okay, human physiology. How will humans cope with multi-year journeys through space? extended exposure to zero gravity, cosmic radiation, lack of reference, okay? Because you can't look out of the big Italian cupola module and see the big blue Earth. You're in interstellar space. You see absolutely nothing but stars, and that might make you go cuckoo. So we might have to put the crew in hibernation like they did in 4 of my favorite movies, and then you freeze them, and then you wake them up when they get to where they're going, kind of like they did in Interstellar, too. The other hazards of interstellar space, radiation is a big one. Even going to Mars, that's a huge one because there's the Van Allen belts and all sorts of radiation that you want to get the people through, otherwise they get radiated to jelly. Dust and small bodies. It's very cold in interstellar space, 2 to 4 degrees above absolute zero. That's pretty cold. And then there's other hot gases and charged particles that your spacecraft would have to deal with. There's no external resources out there. Okay? There's no solar energy available between the stars to do anything with. You can't grow anything. You can't heat anything. I mean, even the New Horizons probe didn't have any solar panels on it, the one that went to Pluto, because Pluto's too far away. Once you get to about Jupiter, or once you get past Mars, there's not enough solar energy to really do a lot with. So you have to carry some other power source. So even the New Horizons probe had a little RTG generator on it. So what kind of power systems would you need on a starship to maintain, the food and the people and that sort of thing? And there's also been some concepts where we can mine, lunar regolith for rocket fuel, or we can make it out of the Mars soil, or go scrape it off of Jupiter's atmosphere. Can't do that in interstellar space. There's no planets. Okay, so how do you get? You have to take all your resources. Okay, emergency plans. Abandoned ship, and you're halfway to Alpha Centauri. Where are you going to go? Okay, yeah, good idea. The ship's blown up, let's get out of here, but you're kind of stuck. So your little individual life raft has to be an interstellar craft on its own, and kudos to anybody that can name the shuttle on the right. Anyway, another one is intelligent, reliable, autonomous systems. We need the HAL 9000 with an iOS upgrade to make sure everything runs okay. Something that's self-learning, self-repairing, and obviously close encounters. Would we be ready if we encountered, one of those guys out in space? So there's all kinds of other things we have to consider here. Okay, so now let's move into the rocket science basics, and this is where it gets a little, engineering-like and a little kind of nerdy. But it'll give you some idea of what we start looking at when we start considering the performance of these kind of engines. The first thing is this is all based on conventional propulsion science. This has all been stuff that we've known for 100 years or more, okay? When you deal with spacecraft and space velocities, or space propulsion systems, you talk about something called delta V. And so in the context of these particular parameters, I'm putting what you need in an engine if you're going to do an interstellar system. So you need an engine that produces a high delta V. Well, what the heck does that mean? Well, delta V is change in velocity. That's pretty much what it means. And so it's driven by the exhaust velocity coming out of the engine times the natural log of the the final mass divided by the initial mass. And this is a very simple science problem. You could stand on a skateboard with a fire extinguisher. You weigh so much, okay, at that whole process. When you squeeze the trigger of the fire extinguisher and the stuff comes out, it's going to come out with a certain velocity and send you in a particular direction. By the time the fire extinguisher is empty, you weigh something different and you're moving at a velocity. That is delta V, okay? So in a sense, what delta V means is how much change in velocity does your engine need to provide in order to get you to a certain speed, and that the mass difference over there represents the amount of propellant you're going to consume. So this little equation right here is why we do not have single stage to orbit. It's why rockets look the way they do. It's why we have staging and why we've been doing things the way we've been doing. This is a very difficult equation to get around. But anyway, if we're going to be having an engine that's going to send us to these extraordinary speeds and extraordinary distances, we need something that's going to be very efficient, right? A very high delta V, that can get us there very efficiently. The next one, let me just show you this chart on the bottom to give you an idea of what the kind of delta V numbers it takes to get from, say, from the ground to Earth orbit. All right, it takes 10 to 15 kilometers per second. Mach 25, if you've heard of that, that's how fast the space shuttle's going, okay, when it orbits or when it orbited, right, back when it was active. Mach 25, 30,000 feet per second, that will put you in low Earth orbit, okay? So if we want to go to Alpha Centauri in 40 years, it's the one up from the bottom that says slow interstellar, we need an engine that puts out a delta V capability of 30,000 kilometers per second. And we're still at the 10 to 15. That's where we are right now. So again, a couple more zeros, a few more dollar signs, and we'll be able to take care of that, no problem. Yeah, right. Okay, so anyway, you know, we have some issues here with this that we have to deal with if we're going to get this kind of performance. The next one is called specific impulse, and we want an engine with a very high specific impulse, okay? So you might have heard this term in the rocket engine or rocket arena or some propulsion aspects, but basically it's exhaust velocity divided by gravity, and there's all kinds of goofy calculus derivations. You can expand this to all sorts of things. But it's weird because specific impulse is measured in seconds, in units of time, and it's measured like efficiency. So for example, the definition right there is the time to burn 1 unit mass of propellant while producing 1 unit force of thrust. So how long does it take to burn a given mass of propellant? So for example, the engine on the Atlas V rocket here on my tie clip, it's a Russian engine called the RD-180. It puts out about 980,000 pounds of thrust. If I were to take this engine and throttle it down to make 1 pound of thrust, how long would it take to consume 1 pound of propellants? All right, and the answer is about 440 seconds. Okay, so you know it's actually about 385. I'm sorry, a little bit less. But anyway, it's a pretty, you know, that's the kind of the units that it would take to describe this. So the higher the specific impulse, the more propellant efficient the engine. It's using its fuel very efficiently. Obviously, we need something that's going to produce stable and continuous thrust. Thrust is just a force to get you going, like F equals ma. Deceleration is also important because if you want to stop somewhere, like you want to go to Alpha Centauri, you need to be able to turn your spacecraft around and fire the thruster in the other direction to slow you down. Otherwise, just like New Horizons, you'll whiz right by. So you need to have this engine that can produce the delta V that you need to get to a certain velocity and stop you at the same, when you get to where you're going. So it's a cumulative effect. So stable and continuous thrust, obviously these engines might be running for days, weeks, months, or years, so you want to make sure they don't break down. You also want to have a high thrust to weight ratio so that the engine doesn't weigh 90% of your space vehicle. That would be impractical. So something that weighs a very small fraction would be good. And then finally, excellent reliability. As I mentioned, these things are going to be operating in harsh environments, running for extremely long duty cycles perhaps, so you want to make sure that they're very reliable. Okay, so now that you guys are all basic rocket scientists and understand these parameters fully and completely, we can talk about conventional mass ejection systems. So this is what we've been doing for almost 100 years, right here, okay? Chemical propulsion. This is the state of the art right now, all right, to launch things of any significant size into space. So 99% of all rocket engines operate on chemical combustion. You put the fuel and oxidizer together, you put them in some kind of a rocket engine chamber, and out comes a lot of hate and corruption, and your vehicle goes up into the sky. Solid rocket motors, basically a big firework, okay? Big firework, like a 3 million pound thrust firework, okay? So it operates with hardly any moving parts and just burns a solid propellant. This is all proven, all right? We know that this works, okay? So is there, what is the best available today? So these are 3 engines that operate on liquid hydrogen and liquid oxygen. That's the most energetic chemical combination that is, I should say, readily available that we can come up with as a human race right now. There's other things, which I'll talk about in a second. But the highest specific impulse we can get out of this combination is 470 seconds, give or take, okay? So these other engines these engines that I'm showing here are all actually flying, or at least the 2 of them are. The RS-68 powers the Delta IV at about 750,000 pounds of thrust. The one in the middle is the RL-10. That's actually engines designed in 1958. Looks the same today. Okay, so we haven't really evolved that engine a whole lot, but that was my bread and butter for about 8 years at the company I work at. It's upper stage engines. It's an upper stage engine, so it doesn't need as much thrust. 23,000 pounds. And then the last engine is the one that was flying on the shuttle, the Space Shuttle main engine at 500,000 pounds of thrust. So that's the best we can do today. Now that last one on the far right there, the Space Shuttle main engine, the most complicated rocket engine ever made, hands down compared to anything that Russia's done. All right, it's an extremely complicated yet extremely reliable, very, very well-performing engine, made right up the street in Canoga Park. Okay, so options for chemical propulsion. What can we do? Well, improvements to this are a lot easier said than done because improvements are basically going to try to squeak out a couple more seconds of ISP or squeak out a couple more pounds of thrust, all with the point, or all with the risk of approaching their design margin and making the thing blow up because you're just trying to push too much performance out of them. So there's ways you can increase the propellant density maybe, where you can say, instead of using liquid hydrogen, maybe I'm going to use slush hydrogen, which is kind of a snow cone. All right, so you're going to take something that's minus 428 degrees Fahrenheit and make it even colder, and then store it, and then burn it in a liquid form when you're ready to burn it in an engine. All right, so we can make slush hydrogen. It's not easy, it takes a lot of energy, but we can do it, all right? And when you start increasing the density of the propellants, you can start increasing the payload you put on your rocket. So that's pretty much all that means, right? Smaller tanks, etc. The second option is by increasing the specific impulse by using things like high energy density materials or fuels instead of the liquid oxygen, liquid hydrogen. For example, metastable helium, all right? Who knew helium could burn, right? But when you have metastable helium, you could burn it and get 3,100 seconds of specific impulse compared to our little 470 from the hydrogen. That's pretty good if you can contain it and if you can get it to last outside the laboratory, all right? Same thing with metallic hydrogen. So John Cole at NASA Marshall said, well, let's take the theoretical core of Jupiter, make a rocket fuel out of it in a lab, produce it in mass quantities, and maybe we can make an engine out of it, and that'll produce 1,700 seconds, okay? So again, some ideas have been looked at these things. These really aren't producible in mass quantities. They're kind of more of a laboratory experiments and so forth. And sometimes the combustion products aren't gaseous. They're solid. And so they start eroding your engine, which is not a good thing if your engine's supposed to last for a couple years. So anyway, either option would require significant changes in infrastructure and technology, a whole new launch, billions and billions and billions of dollars. So regardless of the reactants, no matter what you put together, no matter what we can put together that we found on this Earth or the new elements we can make, if we're going to try to burn things to add the energy to the system, basically we would need more chemical propellant than the mass of the known universe to send something to Alpha Centauri in 900 years. So that's just bad news all around. Okay, so there's no easy way to say, let's just put big rockets on the thing and accelerate it and get it to Alpha Centauri. It ain't going to work. All right, just the physics isn't there. So what else can we do other than chemical burning of propulsion? And that's where we get into alternative mass ejection systems. Okay, alternative systems, these are kind of cool. We're talking nuclear fission, nuclear fusion, and then my personal favorite, matter-antimatter, okay? So basically we're going to add heat energy to some sort of working fluid using other means other than combustion, other than fire, okay? Obviously nuclear stuff heats a lot. It's a lot of heat. Nothing's burning in a nuclear reaction. It's just decaying and doing other things. You're breaking molecular bonds, you're forcing them together. That's releasing a lot of heat. So, for example, nuclear fission, obviously been around for a long, long time. You're breaking apart atoms into certain things. Nuclear fusion, it's always right around the corner, okay? It's the holy grail of energy technology. It's where you're going to slam two things together. It releases a whole lot of energy and makes something new. And then finally, matter-antimatter, which it's not science fiction. We've been doing antimatter for 50 years, okay? And we'll talk about that in a little bit more detail. The nice thing about these options is, okay, if we look at the little hydrogen-oxygen bar on the far left of that chart at the bottom, that's basically the energy density of the best thing we can do right now when we burn things, okay? Now look at how high the bars are on the other ones, right? So basically these are 7 to 9 orders of magnitude higher in energy density for a given amount of stuff. So they put out a lot more energy. So maybe we can do something with this. So we'll talk about some of the things that have been tried and some of the things that are being looked at. Okay, solid core nuclear fission. This was done a long time ago. Look at the dates, 1961 to 1972. This was an extraordinarily successful program for nuclear engines in space. And essentially what it is if you look at the middle picture there, it says liquid hydrogen tank. You run it through a pump. You pump the liquid hydrogen down through a set of nuclear fuel rods where it gets heated up, and then you send that out of a nozzle. So the only moving part is a single pump. There's no fire. There's nothing of that sort. But the amount of energy that you put into that system allows you to get specific impulses like 850 seconds, with growth to like 1,100 seconds. Which remember, 470 is the best we can do now. So now we're going to be almost 3 times that with today's technology. A lot of technology and a lot of money was spent on this, all with extraordinary success. And then someone came along back in those days and said, hey, I got this great idea for this reusable orbital thing. I'm going to call it the space shuttle. And then was like, oh yeah, let's do that. And then they abandoned this. Okay, so there are still parts of this around, these engines, from this program. Dozens of engines were fired all the way up to the scales of 250,000 pounds of thrust, big engines. And there's such a huge history about this program. It's really, really phenomenal. I'm not sure why we're not doing it today, but soapbox. The other version of this is called the particle bed reactor, where instead of having linear fuel rods where the propellant goes down in just a straight line out, it goes over a set of BBs that are all some sort of nuclear fuel. Okay, this was a neat concept because it really compactifies the heavy reactor that you need as part of the engine. The problem they ran into is that it generated so much heat that all of these BBs melted and fused into a big ball of goo, and then nothing passed through it. So there were some design issues to try to figure out why, and then that all got abandoned back in the 80s. Nonetheless, still a pretty neat idea. Okay, gas core nuclear fission. We've only been experimenting with this. It's where we take specific gases and we put them into a chamber, and then we send in a large amount of energy to get the fission process going, and then all you do is just pump in the gas, all right, and it just keeps fissioning and fissioning. So the first one is called open cycle gas core, where you have the fission products up in the center of that toroidal thing there that's surrounded by magnets and so forth. What's neat about this is you can launch it off. So the individual gases, the propellants you actually use to fission, are actually non-radioactive. And then when you start the process, the whole process becomes radioactive. So, it makes the EPA folks very happy. The downside of this is that when you pass the working fluid directly into that container and then out the back, you're passing it right through all that irradiative nasty stuff and sending it out the back. So now you have this long trail of irradiated exhaust that if your crew is following you in another spacecraft later, they might be a little upset, okay? Nonetheless, 3 to 7,000 seconds of specific impulse, pretty neat. A way to get around the whole irradiated exhaust bit is to put the fission products inside a closed cycle gas core concept where you put all of that inside of a big quartz light bulb, and then you pass the working fluid over the light bulb like a heat exchanger, so then there's still hydrogen coming out, but you lose the performance. And so you can see the specific impulse isn't as high as the open cycle, but nonetheless, it is a very good concept. Nuclear fusion. Okay, so this is where we're going to bond atomic nuclei by overpowering electrostatic repulsion. All right, so we all know it's hard to put two south ends of magnets together or two north ends. They want to push each other apart. Well, electrons do the same thing and protons do the same thing. Okay, so if you can overpower it and force these things together, you get not only the loud bang, but you get an enormous amount of fusion energy. Okay, so what's interesting about this is you create a plasma, and that same thing with the fission, but let me tell you, a plasma is basically ionized gas, okay? So even the fluorescent lights that we've been around for decades, inside of that glass tube is a plasma. All right, that's why you have an electrode at either end, and it energizes the gas and makes it electrified, and as soon as you get rid of the electricity, the plasma cools and disappears. Well, the same thing goes on in a fusion reactor. You have to create this plasma, okay? The downside about a plasma is that if it touches something like a container, it'll cool, and then a cascade effect will stop the whole thing. So when they do these kind of plasma things, like I'm going to show you here, they have to make sure that that fusion process, the going on in that plasma, doesn't touch the wall of the container. So how they do that is they put a bunch of big heavy magnets and electric field configurations and all this big heavy stuff around it to magnetically suspend this charged gas in a magnetic field inside of the container. That takes energy, and it takes a lot of special design work and so forth. So anyway, containment and sustainment are the two main issues of trying to do fusion. How do you contain the plasma so it doesn't cool? How do you sustain it? Because if it can't touch the wall, it's very difficult to get the stuff in there, right? To keep fusioning. Is that a word? But anyway, we have basically we have to try to yield greater than 1% of the energy required to sustain it. Ultimately, fusion was the break-even point, right? Where you put in as much energy into the fusion reaction, you get the same amount of energy out. Right now, we've only been able to get about 1% more out than it takes to sustain it, all right? So the Joint European Torus achieved like a 60% initial output for about a minute back in 1997. I don't know if they've really accelerated this a whole lot, but I think maybe you've seen some articles about Lockheed coming up with their nifty fusion device, and there's some other places that are looking at it as well. But it's always just around the corner, okay? So there are three main approaches to looking at nuclear fusion. The first one's kind of an old school one called a tokamak reactor, where it's kind of a donut that's hollowed out within the donut. And you can see on the far bottom left there's these big magnet rings around the outside, big magnet rings in the middle, all to keep the plasma from touching the walls, which you can see in the photo in the middle. That pink film that you see is the fusion plasma that is not touching the walls, okay? And if someone were to stand in that chamber where this photograph was taken, the person, normal person would only be about a third of the way tall in there. This is a huge device. All right, it's about the size of this room, all right, to actually make that fusion device. And then someone said, all right, well, let's just cut the donut in half, straighten it out, and put all the magnets in a line and put a nozzle on the back and make an engine out of it. So cool. So now we have this magnetic confinement fusion engine. Another way of doing a fusion is called inertial confinement. Okay, so inertia means there's something moving that's trying to cause this thing. So essentially, you take a tiny little pellet over in the upper left. The process is you blast this tiny little pellet of fusible material with photons of extraordinary energy, like petawatt type of energy, and then it fuses into this big blast, and then you have fusion. Okay, and someone said, awesome, let's take a couple petawatt powered lasers in space. I'll leave that with you for a second. Heat this stuff, whenever the petawatt powered lasers fire on this pellet, it heats it up to 100 million degrees, it fuses, and then we can make an engine, and that's what's on the far right there. All right, so you're fusing this little pellet by bombarding it with photons at the petawatt level, okay? The other one is called inertial electrostatic confinement, all right? And so we're taking the inertia of something again, but electrostatic, and that kind of means static electricity type of base, or where you have this voltage potential, you get sparks, and you get all kinds of fuzzy things under fuzzy blankets. Same basic process here. You take these rings that you can arrange in kind of like a basketball, sort of like in the middle photo there, and you change the voltage potential across the rings, you feed in some fusionable material, and you can create a little fusion ball inside of these metallic rings. So the nice thing about that is that it doesn't take a whole lot of energy to do, but there hasn't really been a good application for this yet, all right? Someone really hasn't thought of a good way to make an engine out of it because it's just polluted with neutrons, which are bad for fusion type of work. So anyway, there's 3 ways of doing fusion, all of which have been explored. Okay, my favorite of these alternate systems is matter-antimatter, okay? Now, matter-antimatter, again, as I said, is not science fiction. It's been around for a long, long time, okay? Now, what I mean by that is that we all know there's electrons, and electrons have a negative charge, and they orbit a proton. That's basic atomics. Well, an electron also has an antiparticle, which is the same mass and everything, except it has a positive charge. And it has a sexy name called a positron. All right, sounds cool. There's also an antiproton, which is a particle, the mass of the proton, but has a negative charge instead of a positive charge. And so what happens is if you put an electron and a positron together, they annihilate completely. And if you put a proton and an antiproton together, they annihilate completely. It's the most energetic process in nature, is a matter-antimatter collision. And so, for example, 1 kilogram of matter and 1 kilogram of antimatter, so basically 4 pounds of stuff, will produce 1.8 times 10 to the 17 joules. And what does that mean to us? Well, that number times 10 to the 17th is the amount of energy that hits the Earth's surface every second from the sun out of 4 pounds of stuff. Okay? Okay, now we might be getting somewhere, all right, for having a power source to power whatever engine it is we have to take us to the stars, okay? That is an extraordinary amount of energy. Antimatter can be stored using magnetic fields, but you can't touch it with normal matter. Remember, it's negatively charged, but it's completely opposite. If you try to pour it in a bottle, it's going to annihilate. And the Earth, the whole universe doesn't come to an end and all that kind of stuff you've heard from way back when. That's totally false, okay? But just like a plasma, you have to suspend antimatter from touching anything. Otherwise, it will annihilate. In a little tiny flash of light. It doesn't mean the whole lab blows up, okay? So anyway, it's challenging to do, is to suspend mass instead of these, instead of plasma like before. So grams of antimatter could propel a spacecraft to Mars in a month, but creating grams of antimatter could take millions of years. Creating antimatter is actually pretty easy to do. Capturing it is the really, really hard part. And I have a slide in the backups that talks about it, so I won't go into it here. But it's essentially a very inefficient creation process. The global production of antimatter is 2 to 20 nanograms a year, and a nanogram is the mass of a human cell, and a cost of between 25 billion and 300 billion per milligram. And I don't think we've ever made a milligram of antimatter. That's how little of it we can actually capture, okay? So someone said, well, let's say we have this giant tank of this stuff, 55-gallon drum of antimatter, what can we do with it? Well, you can inject antimatter into any working fluid, it'll annihilate and generate a whole lot of energy for you. So that's exactly what these folks did, is they said, here's our containment vessel on the far left, actually built by Penn State back in the 90s, worked out very well, very cheap. They can put antiprotons in this thing. It's about this big, ship it across to CERN in Switzerland, and pull out a few antiprotons. Pretty neat. So now we have basically the warp core of the Enterprise, where we have an antimatter tank. We magnetically confine it and steer it down into something where there's working fluid like a hydrogen, and then we pass it out of a nozzle. So that's pretty much an antimatter engine. And there's an artist's deception of what it would look like on a spacecraft on the far right. So what's nice about this is antimatter has a specific impulse of between 5,000 and 10 million seconds. That's huge because of the amount of energy you get out of this stuff. Okay, so that would be something that would be viable for interstellar missions, multi-decade, and so forth. Okay, other alternative mass ejection systems. Back in the 60s, there was a guy named Robert Broussard that came up with this thing called the interstellar ramjet. The concept was that back in the day, they thought that in the interstellar medium there was an extraordinary amount of hydrogen. And so why not just fly through this hydrogen, scoop it up like a jet engine does, burn it or mix it with something or heat it up somehow and then just spit it out the back, and we don't have to carry any propellant with us. We just suck it out of interstellar space. Okay? Well, as we started learning more and more about what space is and the kind of stuff that's in space, we found out that the actual amount of hydrogen out there is so small that you really couldn't do anything practical with this particular type of engine design. For example, if you wanted to capture 1 gram of hydrogen, which you can create in your kitchen sink with electrolysis, it would take a magnetic field to sweep 10 to the 18 cubic meters volume of space. That's the volume of all the Earth's oceans. Okay, to get 1 gram of hydrogen to burn. And that's not going to make you go very fast, 1 gram of hydrogen. Okay, so again, this is a great concept, but because of what we know now based on science, it's just not very viable. The other idea was nuclear pulse propulsion, otherwise called Orion, back in 1947. Basically, after you can see the year there, that's not very far after the first nuclear tests at Trinity and Los Alamos and whatnot. Someone said, hey, great, now we have this big, great bomb that we can go drop on people. Let's take a bunch of them, spit them out the back of a spacecraft and blow them up, and we'll just ride the shockwave. That's the concept behind Orion. You take a couple thousand nuclear bombs into space with you, you spit them out through a tiny hole in this giant shield. It blows up at some distance away from your spacecraft, and then this shockwave hits the shield and pushes your spacecraft with these giant shock absorbers. Archaic, but practical. Okay, as far as a propulsion system goes. So you can get 100,000 seconds of specific impulse of this. It's I wouldn't even want to begin to know who would want to ride on this as a test flight. But you can get theoretical velocities of about 1/10 of the speed of light. Now, there's been other concepts looking at mini Mag Orion and Mag Orion, where they're trying to not only capture the actual gaseous shock wave from the explosion, but the intense magnetic field that comes along with that as a nuclear explosion. So there's all kinds of people that have looked at this, and the math works. I mean, it is a very basic engineering kind of a brute force approach, but it just doesn't make a whole lot of safety sense or engineering sense. All right, so looking at where these all fall, and I'm not going to go through this, but chemical is kind of where we are. That's pretty much all we got right now. Okay, none of the other engines I've talked to you about have ever flown. That's the delta V, the thrust, and the specific impulse for all the concepts there. Not going to go through it in detail, but that's just for your reference. So where are all these things is with respect to their maturity. You've probably heard of the NASA Technical Readiness Scale. It's basically a 0 through 9 scale, where 0 is 2 guys at a bar drawn on the back of a napkin after a couple drinks at a conference going, hey, I got a great idea. 9 is we've been flying them for decades. Okay, so obviously chemical propulsion is a 9. Interstellar applications are basically impractical with chemical propulsion. And if we move on down the line, I give a 5 for solid core fusion or fission, 3 for fusion, and down at the bottom, matter, antimatter with a 1. All right, because we have experimented with antimatter, but very, very, very little experimentation with actually any kind of propulsion system. So the bottom line is that conventional mass ejection systems, anything where there's something coming out of a nozzle to move something forward, really just aren't viable for this kind of missions within a human lifetime. It's just not going to work. The energy is just too low. The speeds are too low to get those. So yeah, they might be efficient, but we're not going to go anywhere near the kind of speeds we need. So as I mentioned before, or as I mentioned in the yellow box there, they're not going to work for interstellar missions. So we need a paradigm shift, so a completely different way of thinking outside of the brute force fire and brimstone and pumps and nozzles. We need a different way of looking at propulsion. And that's when we're going to move into the physics-based concepts. I'll take this opportunity for a break. Okay, now as I mentioned at the beginning, or as I said before I started a couple of those sections before, there's a few charts I need to go through to kind of prep your mind for some of the stuff you're going to hear about for these concepts. There's some definitions and some caveats and so forth. So what's different about these physics-based ones? Okay, well, there's no propellant, there's no mass ejection. You're not going to send propellant out of the back of anything. Okay. So what does that mean? It's propellantless, all right? Do we have propellantless propulsion systems today? Absolutely, a sailboat. Gotcha, all right? So, and there's a couple other ones, like a skateboard, okay? So terms like specific impulse and delta V that rely on exhaust velocity are meaningless. You don't care about those anymore. So some of these concepts are going to use something called the space-time medium, and we'll go through a lot of these definitions in some level of detail, as the working fluid. So instead of having a big tank of hydrogen, you're going to use the area, the space-time around you, or the tank of space-time or whatever. Propulsive forces are derived from things like fluidic space, quantum physics, string theory, and a whole lot of others. Not all at once, okay? But those are just different concepts that are looked at. Some concepts of propulsion I'll look at, okay, well, if dark matter is this explanation, then maybe we can make an engine out of it based on these particular aspects. Gravity waves, black holes, alternate dimensions. Obviously, these are all highly speculative, as you can imagine, okay? But they have all strong foundations in current scientific knowledge and experimental observations, especially since we're starting to get some of these experimental observations, fairly rapidly and with the kind of resolution that we need. So these concepts can not only propel a vehicle at very high sublight speeds, 70 to 99%, but the speed of light or beyond. And you see everything I did with PowerPoint to those last two words there, okay? Because we've been taught that nothing can go faster than the speed of light, right? That's what we've been taught. That's what we observe in nature. Interestingly enough, Einstein and the folks that came up with all of those basic terms never said that nothing could go faster than the speed of light. That's our interpretation of those things that made it into the mainstream physics. In fact, there's been physicists that have gone back even as recently in 2012 and 2013 that really took a look at all of those calculations. And there was never anything that said that Einstein said, well, that's just not going to work about faster than light. It all said, well, that will work, but that's not the focus of where our science is going right now with the discovery of the electron and the proton. We need to focus on things that are, more aligned with what we're seeing in scientific observations. So the speed of light or beyond is something kind of, very compelling in the fact that the math is there. The math says it can work. There's no mathematical reason why it can't. And we'll talk about that in a little bit. But this is really what we need for interstellar missions, is something like that, the speed of light or beyond. Okay, we're not going to take the rocket engine and accelerate to 99% the speed of light and turn on the big thruster and jump right over, right? It doesn't work that way. So now for something completely different, and here's kind of where these definitions come into play. Space-time medium, that's the three spatial and one temporal dimension in which all things exist, right? There's space-time between Earth and the sun, there's space-time between you and I, and there's space-time between the electron and proton inside of your right fingernail. Okay, there's space-time everywhere. It's the medium by which all things exist. And you've seen that kind of a diagram like at the top where it's kind of this mesh, and then there's the Earth sitting in it, and the mesh is dented, so that kind of represents gravity. Okay, that's called Minkowski space-time, but that is a very easy way of looking at it. Negative mass and negative matter. And again, these are all just definitions to prep your mind for what's going to come in a few charts. Negative mass and negative matter is not antimatter. Okay? Negative mass and negative matter is matter that actually produces a repulsive gravitational effect. All right, or it has a repulsive effect on normal matter. We've all been taught and we all know that everything that we've ever seen attracts in some way. All gravity and so forth attracts each other, and all the galaxies and whatnot. There's some sort of mutually attractive force there. Well, negative matter will have a repulsive force to normal matter. So again, we'll talk about that later. Again, antimatter hasn't really been defined yet as having a repulsive force. So it's not the same. 0-point energy and 0-point field. This is an interesting one, okay? Because basically this says that at a small enough scale, there's enough energy in the vacuum of space to actually do work with. And that was led by this thing called the Casimir experiment, or the Casimir effect, where you take these two tiny plates that are about 1 centimeter square, and you put them apart about, what do I have here? You space them at 1 micron, all right? And in a very controlled environment where there's no other radiation coming in, there's no other electromagnetic waves, there's nothing, these plates will come together, all right, with some unobserved force. And they'll come together with a force of 10 to the minus 7 newtons, which is actually pretty good for something that's that small. And people have thought, oh, cool, let's take, a couple of trillion of these plates and put them together in a room and make this big Casimir generator. It's a good idea, but there's some challenges behind that. So basically what this 0 point says is that the smaller you look in space-time, the more energy you see. And for example, that's why the Large Hadron Collider is called the Large Hadron Collider. It's huge because it needs so much energy to look at such a small scale. And the theory goes that if you need that much energy to look at that scale, then you can extract that much energy from that scale. Very interesting viewpoint for space-time. So there's things like quantum foam and all kinds of things that are at this 0 point energy level that we are theoretically able to extract energy from. String theory. Nobody knows what it is except for about 3 people that all wrote books so that the other 2 can read them, okay? So basically what this says is that everything in the universe is comprised of a little string that vibrates or wiggles or ties itself into a knot, and then, if it ties into a bowline, you get a proton. If it ties into a slip knot, you get a positron. So, things of that nature. Obviously, that's extremely simplistic, but these things are tiny, 10 to the minus 35 meters, okay? So a 1 and 35 zeros before it. That's awfully small, okay? So anyway, that's string theory, and I'll talk about that a little later. And if you take a giant cosmic loom and you take all these strings and you weave them together, you get what's called a membrane, or brain for short, for some of the advanced physics advanced theorists. They call it a brain or a brain world, and our universe exists on a brain of strings that interact with other brains of strings through something called gravity. And these other brains may only be separated by ours by about 1 millimeter or so. Weird stuff, 10 dimensions and 25 dimensions, all kinds of stuff, right? But anyway, the point being is that there's thoughts that there are these alternate dimensions, and who knows what they look like or how they're defined, or if there's any kind of beings in them or whatever, but nonetheless, that's how these 2 things come together. Okay, so things to remember when we talk about these new concepts. We don't understand the true nature of space-time at all. We have no idea what it is. We don't know if it has a fluid-like property, which we think it kind of does right now. Is it pure 0 point energy? Can we get energy from it? Can it be manipulated without using mass? We have no idea, all right? We don't know, meaning the human race, we don't know the nature of mass, all right? But what about the Large Hadron Collider finding the Higgs particle? All that did was check a box in a model it's called the standard model of all the particles. We still really have no idea how the Higgs particle creates mass, or if really that's what it even does. All right, all the model said was, there's this particle that's missing. Let's go find it, and they found it. But we don't really know what interacts and what creates mass. We really don't know the nature of gravity and inertia. I mean, we see it every day. I mean, I'm obviously not floating, and you guys are sitting, so it works, right? And we accelerate when in our car, we can feel ourselves accelerate or step on the brake, but we have really no idea what is causing that interaction from a space-time standpoint. Yeah, there's F equals ma and all that. That's the gross big picture. But what's going on at the space-time level, we don't know. Is it caused by gravitons? Is it caused by a displacement in the space-time continuum? How fast does it propagate? Right? Physicists will get into knockdown, drag-out, ultimate fighting championship Thunderdome cage matches over whether or not gravity acts at the speed of light or gravity acts instantaneously. We don't know. All right, so very interesting. There's also no model that explains everything, and by everything I mean all the standard forces of nature. All right, we have the weak and strong we have the weak and strong nuclear force, electromagnetism, and gravity. And so we really don't know how they all tie together. We can get 3 out of the 4, but never all 4. All right, so there's all sorts of ideas there. And then finally, dark matter and dark energy. What is it? How do we synthesize it? Can we make it? Don't know. But what's important is at the very bottom is that Einstein's equations do not discount faster than light travel. That's the biggie. Okay, categories of propellantless concepts, and these are the ones I'm going to go through, but not all of them. I'm going to cover the 3 categories, but not every one in each. Okay, so I'm going to start with space-time warp systems. Okay, Alcubierre's warp drive and traversable wormholes, and these modify the space-time continuum to mitigate the relativistic effects and allow for travel. So the first one, Alcubierre's warp drive, basically says if you create a positive gravity well in front of an object and a negative gravity well behind it, you can kind of ride this space-time wave through the universe. okay, with whatever's in the middle of that platter right there, is unaffected by relativity. Well, that's cool, okay, because we don't want to mess with that time dilation stuff. So it's a very elegant approach. It's simple and makes sense. It's been around for a while. There's been a lot of people that have looked at it and said, yeah, the math is good, it's awesome, it works. And, you know, there's all kinds of interesting things you can get out of this. The cons are it requires controllable negative mass, which we have no idea how to create. All right? Sometimes some series say you need 10 to the 67 grams of negative mass. Okay? So like something the size of Jupiter to create, you know, to move something the size of this podium. Okay? That might not be easy to do. You know, it's not really guaranteed to travel at faster than light speeds or even the speed of light because we're not real sure how gravity moves through space-time or any of this. And real-time navigation is kind of difficult or impossible because it's hard to get signals into that platform where the ship is. So anyway, that's how Cubier's warp drive. The next one is the subject of the movie Interstellar, right? Kip Thorne and his colleagues came up with the with the traversable wormhole, where instead of traveling along the green line from one place to another, you can just open the door and step through and you're somewhere else. All right, that's awesome. Because it is instantaneous travel, there's no relativistic effects. The mathematics have been really extensively explained, enough that Hollywood latched onto it. The problem is it requires gigantic quantities of both positive and negative matter, like neutron star kind of gigantic quantities. Enormous magnetic fields, like 10 to the 13 Tesla, which is Tesla's not just a car, it's a measure of magnetic field. For example, the most powerful magnetic field we've been able to create to date is about 150 Tesla. So we got a couple more zeros to add on there, all right? Single point destination, if you know where you're going. Obviously, you don't care about navigation if you know where you're going right immediately because it's instantaneous. And then there's stability issues, right? So if you touch the edge of the wormhole, what happens? You know, where do you end up or where does your elbow end up, okay? So it's really interesting about that because how do you know where you're going if you're not already to put the wormhole there to get to, it's kind of this weird paradox thing. But anyway, there's an artist, you know, that ship should probably look pretty familiar if you saw the movie Interstellar, but that drawing is actually from about the mid-90s. So anyway, that's an artist ship going through a wormhole. Okay, so that's space-time warp system, how to move or warp space-time to get from one point to the next. The next one is called fundamental force coupling, and we're going to talk about resonant energy cavities and something called Mach's principle. So resonant energy cavities, and I have a couple, just 2 slides on this. Basically, it's using electromagnetic fields or quantum fluctuations, pick your theory, in some sort of a trapped cavity to do, and it ends up making some kind of a force. So there's usually all sorts of antennas and toroids. It theoretically works by using differential radiation pressure and all kinds of interesting concepts. Excuse me. There's numerous concepts like the Q thruster, the Kinney drive, the M drive, the Serrano drive. All are based on the same kind of philosophy and theory, all right, with the same structure of their cavities and whatnot. I'll show you pictures in just a second. They are measuring some thrust out of these things at the micro to millinewton level, which is tiny. The pros are that they're similar concepts. These have been examined for over about 100 years, some of these things. There's a lot of engineering approaches existed, some of them patent. Patent doesn't mean anything. Patent just makes it easy for the Chinese to get. That's all that means. Okay, so if somebody says they have a patent on it, it doesn't really mean a whole lot. But some of these are scalable, and if they are real, that's the real kicker. The downsides is that some of these have never been demonstrated in over 100 years, right? So with all the physics and science we've been doing, they still don't work, okay? The theories are very difficult to understand or could be based completely on misinterpretations of known physics, which is unfortunately the case in a lot of these. So some experiments and data remain suspect because of, they're getting this force, but then the neighbor's dog walks by the lab and things start shaking and, oh, wow, this is a great device, propelling us. So, yeah, we have to really watch out for things that make these kind of dubious claims. So anyway, here's some interesting work that's been done. Here's the Q thruster from 2004. The one in the upper right is called the M drive, and then the one below that is called the Kinney drive, which still kind of remains a mystery. But these have been around, especially these latter 2 on the right there. They've been getting some press recently. NASA, Q thruster, we're going to make it to Mars in 2 days, and all this, that is, you really got to read that with a grain of salt. Okay, so because anyway, I'll leave that at your discretion. But anyway, these things have to really be scrutinized because extraordinary claims require extraordinary evidence, right? Okay, Mach's principle. Now this one's interesting too. Mach, the same guy that came up with the speed of sound business, was thinking about crazy stuff like this. He said, inertia is felt by an accelerating object due to the radiative gravitational effects of distant matter in the universe. So essentially what that means is the reason why you feel like you want to go back in your seat when you accelerate in your car is because everything in the universe is trying to keep you where you were. So it's this radiative effect, okay? So the theory goes that if you can change your mass, right, if you can fluctuate your mass, 150 pounds, 100 pounds, 150 pounds, 100 pounds, the universe is going to react on you differently, and you might end up with some sort of push-me-pull-you force where the fluctuating mass would be your spaceship, the ballast mass would be your universe, and you end up progressing in one direction, all right? So it's a really interesting idea. There's experiments in progress, which I'm going to get to. You might be able to get negative energies out of this thing, create a different kind of a thruster called a Mach-Lorentz thruster. And again, there's some cons down there, but not a whole lot. Again, there's some really, really interesting work being done just right up the street at Fullerton. Cal State Fullerton is where the lead guy doing this is. And there's some very interesting things that he's been coming up with using this principle for the past couple years. I'll talk about that in a minute. Okay, the last one is my favorite, alternate dimensions and hyperspace. Okay, so is there another universe that you could go into that allows you to circumvent all of the relativistic problems, okay, and get from point A to point B in a faster than light way? So the first one I'm going to talk about is brain-based Alcubierre drive. So now I've brought back the definition of the brain and brought back that the Alcubierre drive from the first concept that we did. And instead of using this positive-negative matter business to create that metric that you see on the right, we're going to use the different dimensions that exist all around us. So if we can expand the dimensions ahead of us and compactify the dimensions behind us, we can end up with that shape that you see on the right and move faster than light. Not only faster than light, but 10 to the 32 times the speed of light. That's pretty quick, okay? And this is a theory. This was a PhD thesis from a guy named Richard Obusi at Baylor University, and it was a fantastic theory. I mean, it's a great idea, but the cons are it requires the existence of these dimensions, okay? So we don't even know if they exist. How many of them do you have to change, in front or behind? How do you change them in front or behind? Nobody knows, okay? And also from a philosophical perspective, if there's people living in these other dimensions and you want to go get milk on Alpha Centauri, they might be a little upset if you're going to change their cosmological constant just so you can go there, right? So anyway, things to think about. Okay, the next one is called tri-space and the trans-space method of faster than light travel. If you remember back when I talked about relativity, I showed you this chart up in the upper corner here, where it basically was energy coming up the one side, velocity on the bottom, and there's a red line in the middle that may be difficult for you to see, but that's the speed of light right there. That's the speed of light line, okay? So essentially what this wraps up to, because I don't have a whole lot of time left, is that it says that there's actually 3 possible velocities you could have for any given energy state. You could be traveling slower than light, light speed, or faster than light. And the faster than light one is called superluminal space. So theoretically, if you could travel at 3 different velocities, you might be able to exist in one of 3 different separate universes that kind of coexist with each other. And we see 2 of them right now. I'm getting blasted with photons coming at me at the speed of light and no slower or no faster. Yet I am subluminal, right? So who's to say that right in this same space there is not another universe that's kind of invisible to us right now where things are moving faster than the speed of light? Very interesting thought, okay? But what's also interesting is what happens over there at this superluminal realm. Because if you look at that orange line, basically it says that the more energy you take out, the faster you go, the faster you approach that velocity curve. So it's infinite. So the more energy you take out, the faster you go, approaching infinite velocity. And the slower you go, or I should say the slower you go, or the more energy you put in, the slower you go, and you start approaching that speed of light curve again, that red line where it never touches. And that's relativity and all that bad news, okay? So interestingly enough, the only thing that communicates between the sub and superluminal realm may be gravity, where instead of having the ball is sitting in the sheet like I have in the upper corner of the upper right there making a dent, which is the subluminal realm. If you look at it from underneath, you kind of see this bulge in that blanket where you don't see the mass creating it. Okay, so let's think. There's a mass creating a gravitational effect and we can't see it. Now that's 2 things to me, black holes or dark matter. Okay? So if there's mass that exists in superluminal space, it's going to have a gravitational effect in our space and we're not going to be able to see it. Okay, so things to think about. All right, but the mathematics of all of this says that real mass can exist in superluminal space, and it's very weird because I have no idea what it would look like, okay? Because everything has to be moving faster than the speed of light with respect to itself. Crazy. But let's say we can capitalize on this and use it for some sort of transportation. So what we would do is we'd have our starship kind of cruising along in subluminal space at slower than light speed, and we want to get somewhere really fast. So we might be able to engage some kind of a field, drop into superluminal space where traveling at faster than the speed of light is perfectly normal, perfectly natural, and when you get where you're going, you return the field and you pop back into subluminal space. So essentially what you've done is you've taken the bypass around a city versus going through downtown LA all the way up to Burbank. Right? Instead of sitting in rush hour subluminally, you've gone a longer way around but much faster. And you've done that where it's perfectly normal to do that. Okay? I don't even know where that road would be, and I'd like to know if there is such a road. But nonetheless, the velocities are always greater than light speed. All right? So as long as you're always greater than light speed by a lot, you don't have to worry about the relativistic effects. The nice thing is because there's this communication of gravity between both of those spaces, navigation's possible. We will be able to see planets of stars, galaxies, and other things because of the gravitational signature it would leave in superluminal space from the subluminal realm. There's also several theories that exist on how to get into superluminal space, which I unfortunately may not have time to go into. But also there's cons of, this assumes that there's like a fluidic property to space-time, which actually there's a lot of support being lent to that right now. It's kind of difficult to picture in your mind what something moving faster than the speed of light would look like. But again, this kind of circumvents the whole thing of, if a mass in our space and subluminal space were to try to accelerate and go faster than light, all kinds of hell breaks loose. And all the physicists throw their arms up and say, oh, you can't do that. This would happen. You'd see all this. Yeah, but if you do it in a realm where it's perfectly natural to go faster than light, then everything's fine. Okay, so anyway, I'll leave that. I can talk more about this later on. So anyway, this is just a comparison of the concepts, which we're not going to go through, about the trans-space way versus the other ways, because the trans-space method seems to be the most plausible way of doing this, and there's actually some scientific evidence that's starting to back that up a little bit. Okay, so the summary of these propellantless ideas. Basically, these are all NASA TRL 0 or 1, as I mentioned before, if you remember that scale. There's only a few of these that offer light speed or faster than light travel, and those are the 5 that I list there, and some of them I didn't cover, but there's charts on them in the backup. The subsystems required to support this stuff, I don't know how much oil these things are going to take, or when your service interval is, or when you change the belts or timing. Nobody has any idea. But what is interesting is cosmology and quantum mechanics are starting to get intertwined. All right, the scale of the very large is starting to look like the scale of the very small, and that's something that we're just now realizing with things like Hubble and all the satellites we have out there looking at the stars and the Large Hadron Collider and everything we have looking at the tiny stuff. There's some commonality in these realms that we didn't expect to see. But I think what's necessary is an alternate space. We need really an alternate space to do this kind of faster than light travel to make these missions possible. All right, so these are the only ideas that are viable for this faster than light business. So what are we doing about it? Okay, experimental efforts. Back in 1996, from 2002, there was one guy named Mark Millis at NASA Glenn that basically took literally hundreds or thousands of concepts and boiled them all down to stuff that was actually real or doable by funding a little bit. I'm not going to go through this in a whole lot of detail, but there were some experiments that he funded, albeit from a tiny, tiny amount. I mean, $1.5 million spread over 6 years to 16 experiments. That's nothing. I mean, nowadays, by the time you fill out the paperwork, you've already spent your budget, right? So anyway, there were 5 looking at things like wormholes and negative matter and all sorts of things. And there's actually a book that I'll talk about later that covers all of this from the American Institute of Aeronautics and Astronautics. It's that thick. It's called The Frontiers of Propulsion Science, and it basically is the summary of the concepts I talked about, plus a lot more, and I'll mention it in a little bit. Okay, Mach effects. So I mentioned that there was a guy named Jim Woodward up the street that was doing effects of this fluctuating mass. So he actually made a little device, which is in the center lower picture there, that is composed of a series of wafers, kind of like cell phone speakers, the real thin wafers. Those have a characteristic where they kind of can change their mass by charging and discharging in some way. And so he built this ultra-sensitive balance, put the device on the balance, he's measuring forces. And the thing's not spinning around the room or anything, but he's measuring these micronewton type of forces. And everything that he's been doing for the past 15 years says that these are real results. And he's trying to figure out any way to say that, no, it's not this, it's not this, it's not mechanical, it's not air conditioning, it's not the cat walking, it's real results. So really interesting stuff coming out of this. Warp field theory, this is being done down at Eagle Works at NASA. Warp field interferometry, that sounds really cool. And basically what they're trying to show is that by using a series of rings and capacitors that they can warp space-time locally with a low amount of energy, enough to divert light. And if they can show that they diverted the light, the laser light, then they showed that they can actually change space-time with magnetic and electric fields, which would be huge. And so far the results are non-null, which is kind of a weird way of saying it's not zero, but kinda, I guess. But nonetheless, far from conclusive. Okay, but work is still being looked at here. Closing information. Okay, so I want to show you just the two books. The one in the upper left is the one written by Dr. Jim Woodward that's up the street. He's an extraordinary author. This book is about his whole journey through developing the Mach effect theory, how he's been testing it, the kind of results he's been getting, and it's just a really, really great reference for looking at looking at the development of that technology. So I would highly recommend that one. And also The Frontiers of Propulsion Science, as I mentioned before, written by AIAA. It's now in its second printing. Again, it's 200 and some pages or 500 pages of nothing but good stuff like what I talked about just recently. Okay, so some final quotes here. Excuse me, to kind of talk to the skeptics in the room, right? So the quote here, there's practically no chance communication satellites will be used to provide better telephone, telegraph, note that word there because of the time, or radio service in the United States. All right, we're not going to be able to use satellites. And 5 years later, the communication satellite was launched, and or 4 years later, and now we have Twitter and Instagram. Okay, so that's one utility-related quote. The next one is, the concept is interesting and well-formed, but if you want to get a better than a C in my class, mister, it better be feasible. And this is some guy named Fred Smith that came up with this ridiculous overnight concept of delivering packages, right? So where would Amazon be without this? And finally, a calculator on the ENIAC, back in the 50s, first computer, had 18,000 vacuum tubes and weighed 30 tons, and someday in the far future, a computer might only weigh have 1,000 vacuum tubes and only weigh 1.5 tons. And that was in 1949. Okay, so we're not quite 70 years. We're 70 years down the road here, and look where we are with computing technology. I mean, things just completely blew up the way these skeptics initially thought. So, final thoughts: mankind needs to venture into the universe to seek the answers and questions about where we came from and what our fate is. Current propulsion technology and near-term advancements are not going to facilitate rapid human expansion of the solar system at all. Contrary to the popular belief, the speed of light is not the speed limit, and Einstein and others have shown this to be true. A paradigm shift has to happen if we're going to be doing this as a spacefaring civilization that thrives. We need things like superluminal speeds that are achievable through physics-based concepts. And of course, these can be developed within 50 years, and of course, I'll take cash, check, or charge if you want to donate to the fund of developing these things. But the real thing is that open minds and a defiance of convention are essential for the advancement of this technology. So the last thing, I want to just give you two final thoughts here. So many of our dreams at first seem improbable, then they seem improbable, and then when we summon the will, they soon become inevitable. And that was a fantastic quote by Christopher Reeve, the late actor that played Superman, injured in a horse riding accident. But that's a very good quote to kind of wrap up for one portion of the talk. And then the other one is, "You've kindled a fire, and we shall not let it die out, but will bend every effort to make the greatest dream of mankind come true." And that was by Professor Hermann Oberth to Tsiolkovsky, the guy that came up with the rocket equation back in 1929, talking about spaceflight. So with that, I want to thank you for your attention. I apologize for running over, and enjoy the rest of the conference.